You're able to hear me, right?
Yes, ma'am. Your voice is clear.
Yeah. Okay. Explanation. Are you able to see my screen?
Yes, ma'am. It's visible, ma'am.
Yeah. So let's begin the week 7 live interactive session for the course Polymer Concepts, Properties, Uses and Sustainability. So as usual, we'll go into the brief recap of lectures. So this week the lectures were based on viscoelasticity of polymer in polymers, right?
Yes, ma'am.
Okay. So lecture 45 was a introduction to viscoelasticity, where viscous and elastic response in molecular view was given, and then a question was given on what happens in case of macromolecules. So in case of a glassy state or rubbery state or in a melt state, what happens, and then the viscoelastic response, contribution of elastic and viscous response was all discussed, right? And then
Yes, ma'am.
Deborah number was introduced, and then terminal response, or during extreme conditions, like when you're for
See
example, say,
experimental large omega low
yes, yes, when
and
your time is large or omega is low, or when your omega is large and time is low, how's the response? And then elastic, viscous and viscoelastic response, which are again matter of time, how, based on time, it varies, and what happens when a polymer is subjected to creep and recovery was all discussed, right? All
yes, ma'am.
a basic overview of viscoelasticity was given. Then lecture 46 was on thermal response. Again, high temperature response for different polymers. What are the thermal signature in case of polymeric system? And again, here annealing was explained in little detail. And then different instruments for measuring the thermal response. For example, your differential scanning, calorimetry, your thermogravimetric analysis, and then TMA was all given an overview. And then DSC and the response of a DSC curve, heat flow versus your time, was given, right?
Yes, ma'am.
Yes, and then thermal conductivity in polymers was also given, where thermal conductivity of polymers, formed polymers, and then when there are some fillers were all discussed.
Yes, ma'am.
Yeah, this was followed by viscoelasticity characterization, where quantitative measurement of viscoelasticity was explained. For example, static test, which is time independent, right? Whereas in case of
Yes, ma'am.
dynamic test, which it is a function of time. So this dynamic tests are based on both, based on theories as well as experiments based on that, right? And then based on the type of deformation, how the test can happen, and then sample geometry, how do you decide the geometry, whether it is a dog bone shape or a cylindrical, right? Or a film type or a sheet type, that is all decided based on the experience and other variables. And then what are the controlled and measured variables was discussed. And then creep and stress relaxation was introduced, right?
Yes, ma'am.
And then next, lecture 48 was on simple models, right? So your void and Maxwell model was explained, where void model, the creep response was explained, right?
Yes, ma'am. For
And
solids.
then, yes, and then in case of Maxwell model, the stress relaxation was explained. So the response for all elastic solid, viscous liquid or Newtonian liquid, and then the viscoelastic material was all explained. And also these models are based on linear viscoelasticity, right?
Yes, ma'am. Linear model.
Yes, yes. was, and then this was followed by lecture 49, where dynamic mechanical analysis was explained in detail, where oscillatory testing and then how the Maxwell model and its response, based on the oscillatory input. When you give a strain input of oscillatory form like E naught sine omega t, and what will the stress output be? So it will have both the in phase and out of phase components, right?
Yes, ma'am.
Yes, and then your dynamic mechanical analysis, where again here different sample geometries and different fixtures, and how it is rate and frequency dependent, and how it can be measured using stress and strain control, and then temperature control, the range of temperature, and all was discussed. And then the regions of viscoelasticity, where E prime and E double prime, it varies, right?
Yes,
Uh,
ma'am.
yeah. Someone else joined? Yeah, was discussed. This was followed by lecture 50, where damping application was discussed. Right? This was based on the uses. Right? So the energy dissipation during a stress strain cycle was calculated, and then energy storage during a stress strain cycle was calculated. Right?
Yes, ma'am.
Yeah. So energy dissipation is stress into strain rate. It
Yes, ma'am.
you will get into the energy dissipation calculation, and then in case of energy storage you will have it is stress into strain, right?
Yes, ma'am. Half into stress into strain.
Yes, yes. So and then damping vibration, damping of vibration, where the displacement, it reduces over the time, was discussed. And then viscoelasticity of rubber was discussed, where model, standard linear solid model was discussed, right? What
Yes,
was the
ma'am.
other name that was told for standard linear solid model?
I'm Xenia model.
Yes. And how many springs and how many dashboard does that model have?
It has two springs and one dashboard.
Yes, perfect. And then damping materials. There was a discussion on damping materials as well, right?
Yes, ma'am.
And then lecture 51 was on time temperature superposition, where in case of linear viscoelasticity, you can have time temperature superposition. Okay, where the Boltzmann superposition principle was discussed, and then viscoelasticity in polymers and temperature effects were all discussed, and then your uh, and time and temperature equivalence was discussed, and this was followed by how do you shift data when you have a particular set of data for set of data for different time and temperatures. You can make master curves, right? Those concepts were discussed based on the shift factor, right?
Yes, ma'am.
And the final lecture for the week was based on impact and energy absorption, where different type of loading was discussed. You know low, low velocity, and then you had your impact, and then ballistic impact was all discussed, right? And then how failure process start, so which is a combination of the material defects and also the molecular mechanism, which is it's a combination, right? And then energy under your stress strain curve, and then what is a fracture energy, right? Which is the what is fracture energy, do you remember? Someone remembers? Hello, are you all there?
Yes, ma'am. We're there, ma'am.
Okay, so fracture energy was discussed, which is nothing but your energy of the fractured area, right? The exposed fractured area per unit area of the fracture, that is whichever is exposed, right? And then your stress intensity factor, stress in that crack or in the fracture, right? That
Yes,
stress
ma'am.
intensity was discussed. And then your polycarbonate ABS blends and alloys. So what is the alloy in case of this polymers? It is again a mixture of two polymers. Here they are compatible, but they are not completely miscible. Okay, and they may be made compatible also by using a compatibilizer or something, right? That is what is the alloy.
Yes, ma'am.
Yeah. And then your impact strength, and then two different type of testing, the ISOT test and the Charpy test for impact strength was discussed. This was followed by what is the impact strength for different polymers, right? LDP, if you remember, it had very high impact strength, right, of the order of 1000. Do you remember?
Yes, ma'am.
Uh, let's go into the practice assignment. So the question number 1 is, behavior of a polymer is described by Maxwell model consisting of a spring element of modulus 10 part 10 Pascal in series with a dashpot of viscosity 10 part 12 Pascal second. In the solid, 50 seconds after the sudden application of a fixed strain of 1%, what will be the stress? So this is a gate question. So are you able to understand the question?
Ma'am, can you draw a diagram if possible?
You have to draw and tell me. Anyway, during the explanation, I'll show you. So what are the things given in the question?
The spring is given and the dashpot is given.
Yes. So what else is given? They are in series. So how will it be? A spring followed by a dashpot in, right?
Yes, ma'am. It's in series. How will
Series. Yes. You know this parallel and series connection, right? I'll show you the diagram, but let me understand how far you're able to get the point. Actually, this Maxwell model is nothing but a spring and dashpot in series, whereas your Voigt model is a spring and dashpot in parallel. Okay, that is your basic fundamental. Okay, so what else is given? The spring has a modulus of 10
modulus
part 10, 10
10
part 10
Pascal?
pascals, and then dashpot has a viscosity of 10 part 12 pascals, right?
Yes, ma'am.
Yeah, and then your time is given, right? 50 seconds.
Yes, ma'am. And a fixed strain of 1%.
1%. So fixed strain of 1% means what is the strain, actual strain? It's given as 1%. So what is your E? It's nothing but 1 by 100. It's given in percentage, right? So you have to convert it to the numbers. So it is
Point 0.01.
1.01. Yes. So given polymer behavior follows the Maxwell model, right?
Yes, ma'am.
So this is how the Maxwell model looks. So your spring and a dashpot, they are in series. This is your Maxwell model. Okay. Whereas in your Voigt model, this dashpot and spring will be in parallel. Okay.
Okay, ma'am.
In one, there will be a spring, and in another line, there will be a dashpot. Like your resistors in series and parallels, right? It's a very
Yes, ma'am.
similar, very analogous to that. Okay. So this is your Maxwell model. Sigma plus lambda into dou sigma by dou t is equal to eta max into E dot. So you're given the values of the constants, right? Now,
Yes, ma'am.
how do you find this lambda from the given data? Either if you can if you remember the concept, you can find, or else logically also you can find lambda. What is lambda actually?
Relaxation time.
Yeah. How do you find that? This is given in your lecture also. You want to try? Is there anyone else who has joined? Pramod, you are able to remember? Okay. Let me proceed. So,
Sorry, ma'am. Actually, I'm driving. I'm
okay.
just listening to lectures.
Okay, no problem, no problem. Okay. So, what type of question is this? Is it a creep question, or is it a sinusoidal input question, or is it a stress relaxation question? What type of question is this?
I'm stress relaxation question.
How did you find that? Did you see my screen, or
No, ma'am, notes. Notes.
how do you say it is stress relaxation? Which parameter says that it's a stress relaxation question?
Ma'am, strain is fixed, ma'am, so it's stress relaxation. When you fix a strain, then variable is stress, so that's how you do it.
Yes, you are right. So this is a stress relaxation question, right? So you have to give a constant strain input and then find out what is the, you have to solve this equation, right? Solve this
Yes, ma'am.
ODE. So your stress relaxation response is given by sigma of t is E max into E naught into exponential of minus t by lambda. So are all the parameters given in this, in the question, or anything else you have to find? You know this is stress relaxation question because it is a fixed strain or a constant strain, that is 1%, that is nothing but 0.01 is given, and then the material follows Maxwell model, and you have the Maxwell equation here, and the Maxwell response for stress relaxation is also here. Now tell me, to find out sigma of t, are all the parameters given, or is there anything else you have to find out?
Emax is not done.
Emax is not given.
Emax is equal to eta max by lambda, so we don't know lambda back again.
Is it Emax is not given, is it? Then what about this 10 per 10?
Okay, man, modulus. But lambda back again, it's you have to substitute that Emax over there, and
Should we substitute only Emax over there? Lambda is a time unit, right? So if I substitute Emax over there, the unit is pascals, right? There is a discrepancy in unit, right? So how do you find that lambda? Okay, let me proceed. Your lambda is nothing but your eta by Emax. Eta max by Emax. This is your dashpot viscosity by spring modulus. That will give you lambda. Logically also you can find out. The dashpot viscosity is Pascal seconds and the spring's modulus is pascals. So Pascal seconds by Pascal is nothing but seconds, right? That is nothing but time unit,
yes, ma'am.
right? So that is how you can extract information from the given question itself. Okay, but you should know the background. However, based on these things also, you can at least get some clues. Okay, so your lambda, your relaxation time is 100 seconds. And then they've also given t value, right? 50 seconds.
Yes, ma'am.
So after 50 seconds, what is the sigma of t or sigma of 50 is asked. So all the parameters are given. Once you substitute, you will get your sigma stress value after 50 seconds is 6.06 into 10 power 7 pascals. Just your mathematical calculation, it will give you the information. Fine. Okay. Now let's go to the second question. Match the following changes observed in calorimetric analysis of a polymer sample when heat flow is plotted against temperature. So when heat flow is plotted against temperature, what from which instrument you will get this data? Here a different name is given.
It's
Different
DSC, ma'am.
Yes. So this is asking your DSC data. So it is so you have to match which kind of response will be for which one. So your step increase in heat flow will be for what? Exothermic peak will be for what? And endothermic peak will be for what?
And step increases for glass transition.
Okay. Exothermic peak.
Crystallization is exothermic, and melting is endothermic.
Yes, you are perfect. Okay. So your step increase in heat flow is for glass transition. Your exothermic peak corresponds to crystallization and your endothermic peak corresponds to melting. Fine. Okay. Let's go to the question number 3. So this question has two parts. Okay. The stress relaxation equation for polymer is given by sigma is equal to sigma naught into exponential of minus T by tau, where sigma is the stress at any time T, sigma naught is the initial stress, tau is the relaxation time. The relaxation process is temperature dependent and follows the Arrhenius law. Okay. So for a rubber sample, the relaxation time is 60 days at 25 degrees. Okay. So if the above sample is stressed to 2 megapascal initially, then the time required to relax the stress to 1 megapascal will be, so what will be the time for relaxing the stress from 2 megapascal to 1 megapascal? Is it 31.6 days, or it is 41.6 days, or 51.6 days, or 61.6 days? How will you find out this? Hello? Are you there?
Yes, ma'am.
How will you find out this? They have given some stress relaxation equation also.
Ma'am, you take log on both sides and find T from there, ma'am.
You take log on both sides of which?
Both sides of sigma and sigma naught exponential, then give T is varying, so T1 and T2. Okay, sorry, tau is varying, so you can do with that part.
So for the first part, what should be the, what are the parameters you'll be using? They've asked time required to relax the stress from 2 to 1 megapascal. This is the stress relaxation equation they have given. What will be sigma naught? Should we use the given equation for finding out the time required to relax from 2 to 1 megapascal, or should we use some other equation? Are you able to guess anything?
No, ma'am.
So let's proceed. The first part is very simple. Okay. So they have already given the expression for stress relaxation. Sigma is equal to sigma naught into exponential of minus T by tau. Right? And then they have given sigma naught. That is your initial stress is 2 megapascal. And then the stress reduces, or the stress relaxes to 1 megapascal. Right? And also
Yes, ma'am.
they have given your relaxation time as 60 days. This is at 25 degrees centigrade. Okay. For your first part of the question, the temperature is fixed 25 degrees centigrade and your tau is given 60 days. Sigma is given, sigma naught is given. The only thing you have to find out is T. Okay, that is the time required to relax from 2 to 1 megapascal. Right?
Yes, ma'am.
Yeah, because this is stress relaxation, so there will be a constant strain. So obviously the stress start getting relaxed or it starts reducing. So you can find out what is the time. That is 41.6 days. Okay, you have all the other terms. So only thing you have to find out is T. Okay. Now your second part of the question. If the activation energy for relaxation is 30 kilojoule per mole, then what will be the relaxation time at 35 degrees? Will it be 30.5 days or will it be 35.5 days or will it be 40.5 days or will it be 45.5 days? This is again a gate question. It was asked in gate 2012. So what should you use? Which clue you have to take in? That is also already given.
Activation energy part.
Activation energy, okay. But yes, activation energy, yes, it's definitely a clue. Okay.
Is it log sigma by sigma not equal to something with activation energy? A,
One thing you missed out in the, the basic part of the question. So the relaxation process is temperature dependent and it follows Arrhenius law. So either it follows a closer to glass transition. If the relaxation process is temperature dependent, then it follows WLF equation, right? Or else it follows Arrhenius law. So they have given it follows Arrhenius law. So what is Arrhenius law? So your Arrhenius law is your relaxation time is approximately equal to your exponential of activation energy by RT. Okay, this is the expression. It is actually not exactly equal to, but it is almost,
exponential constant would come.
yes, yes. Okay. So this is what is your Arrhenius law. Now what are the information given from the question?
EA is given
Yes,
and T is at 35
yes,
and R is gas constant.
yes. So you
You
can
have to
find out.
find lambda, ma'am.
Yes. So you can just find out. You can just take it in this way. Okay. So for one case, they have given lambda 1 is 60 days when the temperature is 25 degrees. And similarly,
Yes,
for
ma'am.
the other case, they have given temperature is 35 degrees, but you do not know the lambda. But you have the value of E as well as R. So just substituting it, all the terms, the only unknown is your lambda. Right?
Yes, ma'am.
Yes. And also, your E is not given in joule per mole, but it is given in kilojoule. So always you have to check in for your unit consistency. And again, you have to check for your temperature also. It is given in
In Kelvin. You should convert in
centigrade, so
Kelvin.
you have to convert it into Kelvin. And then again, your gas constant you have to consider. So again, your gas constants, you can take it in different units. So whichever unit system you're following, that unit system, that value you have to substitute. Here I have used SI system only. So your value is 8.314 joule per mole Kelvin. So once you substitute everything, You will get your lambda 2 as 40.5 years. Okay? You are able to get it? Hello?
Yes, ma'am.
Yeah. Okay. Now let's proceed to the next question. Notched impact strength of a plastic decreases with, does it decrease with increase in notch tip radius, or does it increase with it decreases with the increase in notch depth, or does it decrease with increase in temperature, or does it decrease with decrease in notch depth? What does it depend on? Shall I say the answer, or you want to think?
Yes.
Okay, let me say. It increases, sorry, it decreases with increase in notch depth. As your notch, depth of the notch, increases, obviously your strength to break it will decrease, right? There is a notch, right? There is an opening, right? You remember the notch, ISO test and Charpy test, that notch diagram. There's a V-shaped notch, right?
Yes, ma'am. We know.
So when you increase that notch, obviously that means your impact strength will, it easily breaks with the lower strength itself, right? The energy
Yes,
required
ma'am.
to break it is lesser. That is what this question says. Okay?
Okay, ma'am.
Yeah. Next. Deborah number is the ratio of dash, and when Deborah number is very much less than 1, then the relaxation process would lead to dash.
Is it time scale of interest to experimental time, ratio of time scale of interest to experimental time, and when Deborah number is less than 1, it leads to dissipation of energy.
Less than 1 leads to dissipation of energy is fine. But the ratio, what you said, can you repeat it?
It's lambda by T experimental.
Yes, but what is lambda?
The same lambda and
Lambda is your relaxation time. Okay,
relaxation.
the time of interest or time scale of interest is nothing but your experimental time. You said both, the similar quantity ratio. Okay, it is
Yes, ma'am.
actually relaxation time to experimental time. Experimental time can also be called as the time scale of our interest. Okay,
Okay, ma'am.
and then as you said, when Deborah number is very much less than 1, then dissipation of energy. It leads to dissipation of energy. It's nothing but your lambda tends to 0, that is instantaneous relaxation, or your experimental time scale is very large. Okay? Okay.
Yes, ma'am.
Creep refers to application of what?
Constant stress and variable strain. Ma'am.
Application of constant stress, and then you measure the strain over
Great.
time. Okay?
Yes, ma'am.
Yeah. Next. Dash refers to use of thermal energy for rearrangement of molecules, crystalline phase, blend domains, and copolymer domains in polymers. Use of thermal energy for rearrangement of molecules, or crystalline phase, or blend domains, or copolymer domains in polymers. What is the process? We just discussed. We just discussed before the session started, and then during the recap also we discussed. What is it? What is that process called? Use of thermal energy for rearrangement of molecules. Let me give you a clue. We also discussed that it not only pertains to polymers but to other materials as well. This process. Are you there?
Yes, ma'am, I'm there, ma'am.
So what is that process? Pramod, if you can type in, you can type in if you know the answers.
Yes, sir. Let me just.
Do you want to think? What is this process? Use of thermal energy for rearrangement of molecules. Nobody is answering? No. It's annealing. We discussed, right?
Yes, ma'am.
Yeah. So you have to remember the process in whatever way it is asked. Okay. Okay. Formed polymers have thermal conductivity dash than normal polymers. Does it have higher thermal conductivity than normal polymers, or does it have lower thermal conductivity, or does it have similar thermal conductivity, or is it none of the above?
Ma'am, it is higher than normal polymers.
Is it higher? Are you sure? Pramod, do you agree? You can just type in the chat box.
Yes, ma'am. Sorry, I cannot up. I'm driving.
Oh, okay, fine. Okay, you're driving. So shoes. It's
No,
actually
no, ma'am, it's lower one.
lower
Point.
than the normal polymers, because again when you foam it, no, there will be air gaps, right? That will further reduce your thermal conductivity, right?
Yes, ma'am. Film-like thing forming. You're
Yeah.
putting.
So for polymer, at least you have some continuous solid, whereas when there is a foam in between, there is an air gap, right?
Yes, ma'am.
So obviously your thermal conductivity will reduce. So it has a lower thermal conductivity than normal polymers, and it's approximately 1 order lower thermal conductivity. Okay.
Yes, ma'am.
Okay. Question: Who can solids have dash compliance, and relaxation modulus for viscous or Newtonian fluid is dash? So this question has two parts. Are you able to get those two parts? The first part is asking compliance of Hookean solid. Second part is asking relaxation modulus for viscous or Newtonian fluid. What happens to compliance?
Ma'am, is it complete compliance, like 100%? Who can solids have 100% compliance?
No. So where does compliance comes into picture? In which experiment compliance come into picture?
When it is under creep, ma'am.
Yes. So what is creep?
Constant stress, variable strain.
Yes.
So
Hookean
Hooke's law is
solid.
followed.
What happens? I'm not asking about polymers. I'm asking about Hookean solid. When there is a constant stress.
Strain will also be. It will take a constant value.
Yes. So what happens to compliance?
Compliance is a ratio of strain by stress, so it will be constant, ma'am. It will be
Yes.
some numerical constant.
Yes. So it is a constant compliance. Okay.
Yes, ma'am.
Constant compliance. So now what about the relaxation modulus for viscous or Newtonian fluid?
When you give stress, fluid will start deforming, so not constant.
Where do you talk of relaxation modulus? Do you speak during creep experiment? Relaxation modulus? Where do you speak of relaxation modulus? You speak of relaxation modulus during a stress relaxation experiment, right?
Yes, ma'am.
So, what happens in a stress relaxation experiment?
More the stress you give, the lower fluid will go back. So compliance should be greater than 1.
I'm not asking of compliance. Here it is a relaxation modulus. That's what the question is tricky about. The first part of the question was asking on compliance of a Hookean solid. The second part of the question is asking relaxation modulus for a Newtonian fluid. So, relaxation modulus for a Newtonian fluid is 0. So, relaxation modulus you speak about when you have a constant strain, right? So, when you have a constant strain, when you just strain a liquid, it instantaneously starts decaying. The stress starts decaying, right? To maintain
Yes,
the
ma'am.
strain, you need not have to maintain that same stress, right? So it's an instantaneous decay. Stress goes to 0 immediately for a viscous liquid, because once you give a strain, it immediately
It will come back to itself only.
0. Yes. So your modulus, relaxation modulus is 0. Okay.
Okay, ma'am.
Yeah. Only when it comes to polymers, you will have contribution of both in both the cases. Fine. Are you able to
Yes,
get the point?
yes, ma'am.
Because once you strain in case of a stress relaxation for a fluid, it doesn't need any stress further. That's all. The stress immediately decays, instantaneously decays, because the strain is maintained. To maintain the same strain, you need not have any stress. So the stress decays to 0. So your relaxation modulus is stress as a function of time to constant strain. So obviously your stress decays to 0. So your relaxation modulus is 0. You're able to get this point?
Yes, ma'am.
According to Maxwell model, for oscillatory response, as the frequency increases, dash response dominates, while as the frequency decreases or at lower frequency, dash response dominate. At, at higher frequency, which response dominate, and at lower frequency, which response dominate. For a Maxwell model.
Ma'am, in a higher one, it is elastic contribution, and in lower one, it's viscous.
Perfect. This is based on this plot. Okay. This is again for a Maxwell model. Fine.
I mean, this one, the blue tick would be on the right hand side or the left hand side, ma'am?
Which one?
Actually, for lambda 2, sir had said that it's 10 seconds. The crossover is for 1 second as per the snip which you have taken. And when lambda 2 increases, he asked to think about whether it will be the left hand side or right hand side. So, is it right or left? The blue tick which is there in the screen.
So, as the frequency increases, your elastic response starts dominating, right? So obviously it will be in the left hand side.
Okay, ma'am.
Okay.
Yes, ma'am.
Also, your time increases. which is inversely proportional to your frequency. So your frequency decreases. So that will happen, this crossover will happen at a lower frequency. Okay?
Okay, ma'am.
Okay, fine. Now tell me, half eta into strain rate square is energy dash during a stress strain cycle.
Ma'am, it's work done, so kinetic energy.
Energy dash during a stress strain cycle. It's a simple answer. We also discussed this during the recap. Just look into the terms and you can identify half eta E dot square. Eta is the clue.
Ma'am, is it dissipation energy?
Yes, it's energy dissipation. So whenever you have eta, no, it's energy dissipation. Whereas energy absorption or elastic energy, when you have E, your modulus. Okay. So
Okay.
eta is a clue. This is actually the expression, the final expression what you get for energy dissipation during a stress strain cycle. Okay. You remember that derivation?
Yes, ma'am.
Yeah, this is the final expression you get for a sinusoidal input. Okay. Damping behavior increases with strong secondary interaction. Is the statement true or false?
Ma'am, false. It decreases with second interaction and crystallization.
Yes,
Crystal.
perfect. Yes, damping behavior, it decreases with strong secondary interactions and crystallinity. Okay, next. Temperature affects all relaxation modes identically. Is it true or false?
Ma'am, is it false?
Is it false? You have to justify why. It's actually true because only if you have that all relaxation modes having identical temperature effects, you can use this shift factors, right? That is what time temperature superposition concepts and all, it was explained, right, in lecture 51.
Yes, ma'am.
And then that is how you get into the concept of this thermorheological simple materials. Okay. So in all relaxation modes, the temperature effect should be identical. And it is almost identical in all the cases. That is what was explained. Hope you remember that. Okay. Next. ISOT test is based on per unit dash of crack. Is it per unit length, or is it per unit volume, or is it per unit area? Hello, are you there?
Yes, ma'am.
You're able to remember? Is it based on per unit volume, or is it based on per unit area, or is it based on per unit length of crack? What it is based on? It is based on per unit length of crack, whereas the Charpy test is based on per unit area of crack. Okay.
Okay, ma'am.
Now let's get into the doubt clarification session. Okay. So in doubt clarification, so Shivakumar, he has posted for asking for solution for question number 16, 22 and 24 of assignment 6. So assignment 6, so two plots were given. One was showing the dielectric loss over a frequency range for a pure polymer, and the other was showing dielectric loss over a frequency range for a polymer blend. Okay.
Yes, ma'am.
Yeah. So question number 16 was, this variation of dielectric loss in the frequency range of 1 to 10 power 6 Hz indicates the following phenomenon. Is it interfacial polarization, or is it molecular polarization, or is it electronic, or is it atomic polarization? So which one does
Ma'am,
it
it's
belong to?
molecular polarization.
Yes. How do you say that? It is molecular or it's molecular polarization process. Okay. Or molecular relaxation process. Simple way to identify is that this frequency range that has been mentioned, it is 1 to 10 power 6 Hertz. Okay. So when you get into the response of materials to electromagnetic radiation, so obviously, this electromagnetic radiation have different, range of frequencies or wavelengths, right? So each of the contribution will be for particular wavelength or frequencies. So this molecular relaxation or molecular polarization is for the frequency of 10 power minus 3 to 10 power 6 Hertz. Okay. That is one of the key, clue for identifying what type of polarization or what type of relaxation it is. Okay.
Okay, ma'am.
Yeah. Now, the question number 22, what he has asked is, relaxation time for the rightmost curve in figure B will be of the order of what seconds? Will it be 10 power minus 5 or 10 power 5 or 10 power 1 or 10 power minus 1? So, this was figure B. So, the rightmost curve, it is having values starting from approximately
2.9 or 3.
2.8 or 3 to almost 6.5 or
6.6.
something, right?
Yes, ma'am.
Yes. So at what frequency is this, is the peak of this curve?
Ma'am, if we drop one perpendicular, then it comes roughly around 5. And that's log of nu is 5.
That means it is nothing but log of nu is 5. So nu is nothing but 10 power 5. 10 power
Yes,
5
ma'am.
hertz. That is nothing but 10 power 5 second inverse. So why did I ask the peak? I asked the peak because here they have given the dielectric loss versus the frequency. So when you look into the dielectric loss versus frequency plot, the peak happens at omega lambda equal to 1, right?
Yes, ma'am.
Where lambda is your relaxation time, right? So
Yes, ma'am.
once you know omega, you can find out what is lambda, right? So omega lambda is equal to 1. So lambda is your relaxation time, and your frequency is nothing but 2 pi omega, right?
Yes, ma'am.
How your frequency is related to your angular frequency. So your time is inversely proportional to your angular frequency. So obviously it is inversely proportional to your frequency. So they've asked for the order. What order of magnitude is the relaxation time? So it is nothing but 1 by 10 power 5, that is nothing but 10 power minus 5 seconds. Okay, you are able to get it?
Yes, ma'am. Yes, ma'am.
So your crux is that you have to get that, identify that your peak corresponds to omega lambda equal to 1. That will give you lambda is inversely proportional to your frequency or angular frequency, from which you can find out what will be the order of magnitude of your relaxation time. It will be of around 10 power minus 5 seconds in this case. Okay,
Okay, ma'am.
sir. And then what happens to your question number 24? In question number 24, what they have asked, there are 5 curves in figure A. The relaxation for rightmost curve is lambda Ri and for leftmost curve is lambda Le. So what is the ratio of lambda Le to lambda Ri? So what will be, it will be closest to? Will it be closest to 10 power minus 4, or will it be closest to 10 power, sorry, will it be closest to 5 or 10 power 4 or 0.2? So you have the curve. Now tell me, how do you identify?
And the rightmost curve is same around 5. Peak of rightmost curve is 5.
Yes.
And the leftmost curve, I would say, is 1.
Yes. So your frequency is 10 power 5 for rightmost and 10 power 1 for leftmost, right?
Leftmost, yes, ma'am. Yes, ma'am.
So here again, it is inverse proportionality. So obviously, your relaxation time for rightmost will be of the order of 10 power minus 5, and for leftmost it will be 10 power minus 1.
Minus 1. Yes, ma'am.
So your lambda leftmost by lambda rightmost will be 10 power minus 1 by 10 power minus 5. So what will be the ratio? Now this is just mathematics. What will be the ratio? I have told you all the steps. Just calculate and say what will be the ratio. You need not calculate. You can just straight away say. Are you there?
Yes, ma'am.
What will be the ratio?
It's option A.
Is it option A? Just look into the question. It is lambda of left to lambda of right. It is option C. 10 power minus 1 by 10 power minus 5. So 10 power minus 5, when it goes to numerator, it becomes 10 power 5. So 10 power 5 into 10 power minus 1 is nothing but 10 power 4. So the ratio will be closest to 10 power 4. Okay.
Okay, ma'am.
Any other doubts? Are you able to follow? Any other
Ma'am,
doubts?
I mean, actually, I suppose there was one gate question. Remember the stress and strain one, which was given for find viscoelastic deformation, elastic deformation with a curve-like thing. The lecture notes. Can you explain that question alone? Ma'am? I suppose it's in the first lecture of this week. There was one gate question which was PQRS type.
Yeah. Yeah, I get you. One second. Let me go into that. This one you're asking.
Yes, ma'am. This one.
See, what happens is that, so they have given a plot of strain versus time. Okay. So what happens is that based on this plot, first what is happening? There is a instantaneous increase to some value, right? It is jumping to some value of P or some value of strain. Okay, you're able to
Yes,
get
ma'am.
it? So that
Yes,
is
ma'am.
nothing but your elastic deformation. When there is an instantaneous, so when you just pull it, when you pull your spring, there is an instantaneous deformation, right? Or when you apply a particular, stress, there is an instantaneous deformation. When your stress goes to sigma naught,
Hmm.
there
Yes,
is
ma'am.
an instantaneous deformation, right? This is what in a Hookean solid. So that similar response is what is P. But this is a viscoelastic material, so the material doesn't stop with that, but there is a continuous deformation, okay, till the application of stress. Okay, till the application of stress, till point B, or till that time corresponding to point B, there is an application of stress. So what
Yes, ma'am.
happens is that in the viscoelastic material, first the spring responds, and then there is an instantaneous or elastic deformation. So this is followed by a viscoelastic deformation, which is kind of curved. Okay, that is a viscoelastic deformation. And then once your stress is released, what happens is that there is a instantaneous recovery due to the elastic nature within the material. Okay, that is what is given in by R. That is the BC line.
Yes, ma'am.
That is your elastic recovery. And
Yes,
this
ma'am.
is followed by the viscous recovery or your viscoelastic recovery, which follows the path of CD. Okay?
Yes, ma'am. But the answer is for C option. So S is 4. The elastic recovery is not straight line.
Yeah, it is.
It's curve path. Because the answer in the last one they said it's C.
Okay, once again, once again, once again. No, it's D. The slide number 5. This is slide number 5, right? It is D.
Oh, okay, ma'am.
Okay?
Okay, ma'am.
So, P is 2, which is nothing but your elastic deformation. And then Q is 1, which is nothing but your viscoelastic deformation. R is 4, which is your elastic recovery. And then S is 3, which is nothing but your viscoelastic recovery. Okay, it is D, it's not C. Okay,
Okay, ma'am.
fine. Right. So, any other doubts? Any other doubts, or let's close the session for the day? Hello?
Yes, ma'am.
So, any other doubts you have, or let's close the session for the day?
Ma'am, there was one question on this one cross polymer link and the AP molecular weight based on amorphous molecular
Yeah, yeah,
weight.
yeah.
Low,
Yes.
that question.
Yeah, wait. I think that was in your lecture 46, right? If I'm. Yeah, this one, right?
Ma'am, you're not presenting your screen.
Oh, sorry, sorry, sorry. Wait, wait, wait. Sorry. This is the question you have
Yes,
asked me.
ma'am. Yes, ma'am. And why is that molecular weight high and low? How is this affecting? That's my question. Like moderate
Okay.
weight,
See,
how is it?
when you have a lower molecular weight, obviously as temperature increases, your rubbery and your uh, ability to lose your modulus becomes higher. So the drop in modulus becomes higher when the molecular weight is lower. So as you increase the molecular weight, obviously there will be some entanglements, so which will resist your segmental mobility. When you have some entanglements and all, no, see, as the chain length increases, or as you keep on adding your monomeric units, you have more monomers, your molecular weight is higher, right?
Yes, ma'am.
So obviously, the material tends to have more of a random coil structure. So there will be some entanglements, right? Or some
Okay.
steric hindrances, obviously, right? So it will resist the segmental mobility. So when
Okay.
your mobility is more only, your dissipation is more. Otherwise, your modulus will be more. Okay, when the mobility is less, obviously your elastic energy will be more. So obviously your modulus will be more, and it will resist, the material to deform. Right. That is why higher molecular weight, it will have comparatively higher moduli after the glass transition also. Whereas the lower molecular weight, it will fall off faster.
Yes, ma'am.
You're able to get it right?
Yes, ma'am.
Yeah.
This, ma'am, this is option is C, right? So it is 2 is down. This one is only C, I suppose. Answer to the question is.
Yeah. C is, yeah. P is 2, your amorphous polymer with a moderate molecular weight. And then Q is 1, your
One
amorphous polymer
high
with a
molecule.
higher molecular weight. And then when there's a crystallinity, again there's much more resistance. So obviously your solid like or elastic nature will be more. Your modulus will be comparatively higher, and then it will fall later. Whereas in case of a cross-linked polymer, obviously your
Everything.
elastic
Modulus is high.
modulus is higher. Yes, for this only it is C.
Okay. Ma'am, and this one, even though crystallinity is there, but cross link is dominating over here.
Yes, cross links, it'll resist, it'll give much more solid like behavior. Crystallinity, obviously, when you cross your TG and your melting temperature and all,
It will become amorphous or.
yeah, it will not become amorphous. Yeah, see, what happens is that there will be a molecular flexibility, and then the crystalline arrangement, once you start going into the melt temperature, because here again it is a temperature versus modulus. So you may reach your, closer to your melt temperature. Obviously, the crystalline regions also becomes weaker.
Yes, ma'am.
Okay.
So we can say cross link is always better in a polymer than crystal polymers. If you say modulus, if you take two polymer modulus, then
Again,
cross
here,
link.
what happens is that this is all, generic cases. Individual cases, you really have to look
No, can
into
we
how
make
it.
it like a thumb rule, like thing like cross link polymer
Yeah,
means
cross
like.
link, it becomes, difficult to make. That is why, in case of your thermoset polymers and all, uh, it goes to a degradation state instead of, your melting and all, right?
Yes, ma'am.
Yeah.
Okay, ma'am. Okay. Okay, ma'am. That's it, ma'am. I have done with my questions.
Okay, fine.
Okay. Thank you, ma'am.
Thank you.